Zoom recording. Oh, so we have to start all over again, but not all over again, just right here. So the first section is chemistry and its methods. The goal is recognize the difference between a hypothesis and a theory and understand how laws are established. I'm going to look at my participant screen and I'm going to ask the question. What's the difference between a hypothesis and a theory? Anyone want to take a shot? Come on, someone be brave. Someone break the ice.
Hi, my name's Jessica. From what I understand, the difference between a hypothesis and a theory is that the theory is well tested and has more evidence, more oomph to it.
That's exactly right. A hypothesis is a little thing where you're actually trying to determine whether or not your hypothesis is true. A theory, you've got a whole lot of evidence backing it up. So that's why they talk about things like evolution being a theory, not a hypothesis, because there's a whole lot of evidence backing it up. So that's a theory. A lot of evidence to support it. So we have something in chemistry called kinetic molecular theory. And that theory is a body of principles that guides us in thinking about the kinetics of molecules. And there's a whole lot of evidence that backs it up. So good job. All right, so here we go. Now I'm not starting with hypothesis and law, I'm starting with what is chemistry. Basically, it's the study of matter and its properties. Like at what temperature does something melt? Does it oxidize? So those would be some properties. Another property is it a solid, liquid, or gas at room temp? Now, why do we want to understand properties of materials? And the answer is pretty simple. It allows you to distinguish between different substances. For instance, if you run into something and you're walking along the street and you see that it's a liquid, you know right away that it's not rubber, right? Rubber's not a liquid at room temp. And when you look at it and you kind of splash in it, it behaves like water, so you think it's water. You sniff it, it doesn't smell like gasoline, so that reinforces the idea that it's water. So you're using properties of different materials to distinguish between one and another. And of course, that's really important because you don't want to be bathing in gasoline, but you do want to bathe in water. All right. Now, a lot of the focus in chemistry is on changing one substance into another substance. And ultimately, the way you know you've done that is because the new substance compared to the old will have a different set of properties. So if you want to change water into ice, how do you know you've succeeded? Well, one of the answers is you've got a solid. All right. This type of activity is useful in life science, physical science, social sciences, medical fields, engineering fields. It's useful just about everywhere. It's even useful in art. I don't know if any of you do any sort of artwork, but when you're working with metal, you're doing a little bit of chemistry. If you've done any glazing, that is a big chemistry project. Because if you know about glazing, you know that you apply the glaze, you heat it up, and it's changed. Okay? Anyone here an art student? Made any pottery and glazed it? Oh, that sounds like a fun thing. All right, we're going to move on. Okay, so I've got two little columns here. Goals of science. They tell you that some of the goals are prediction, control, understanding, and explaining. You want to be able to make predictions with science. By doing a lot of experimentations, doing some preparation, some studying, you may be able to predict the behavior of some sort of chemical so that you can control the outcome. So let's say that you want to make aspirin and you happen to know that you can esterify aspirin. You might have some control over making aspirin. And also for science, you want to be able to understand and explain things. Here's an interesting thing. Well, maybe it's not so interesting to you, but it's interesting to me. When I'm running the water and I'm running the hot and the cold, if it's too hot, I'm kind of the guy who turns the cold water on further to help cool things down. But I always notice that whenever I turn the cold water on higher, immediately the water out of the faucet gets hotter. So how does the water get hotter when I'm increasing the cold flow? And the answer is when I increase the cold flow, all of the water is flowing faster, which means that more water is hitting my hands over the same period of time, but it still hasn't mixed yet. So it feels hotter because the amount of heat per volume of water is the same. So when the water's coming out faster, it feels hotter, then it cools down. So that's kind of the understanding and explaining things. You can use science to explain things that might not seem comprehensible otherwise. Okay, so what are the dilemmas with science? Well, there are many, but here's just a few. Sometimes experiments fail, and therefore you think you have failed, and that's not the case. If the experiment fails, your job is to troubleshoot and to see if there is a fatal flaw with the experiment or a flaw with how you perform the experiment. Sometimes you get outlier data and you have to decide whether to keep that data or to toss it. And you usually have to have a good explanation for why you want to toss something. Sometimes you get two separate interpretations that are valid. And you may find that people argue about that. And lastly, you have these scientists are human. I know. You thought we were superhuman. We're not. We're human. So scientists are vain. Scientists are humble. Scientists are narcissists. Scientists, I mean, you get all sorts of different scientists. And you get along with that, their basic characteristics. And so you'll have some scientists that will defend their hypothesis to the end, and some people that won't defend anything. So what are our solutions to some of these problems? And one is that you got to have reproducible experiments. If someone can't do the experiment you've done somewhere else and get the same results, that's suspect. And you also want to have published peer review. So published, means put it in a magazine or some electronic form for everyone to read, but also peer review. That means that you have subject matter experts that read this and say, you know what, it's worth publishing. It has importance. So these are the things that especially overcome the idea that scientists are human and, some people screw up and some people don't screw up. They just flat out lie. And that's how we deal with it. Any questions there? All right, we're gonna move on. Next section is sustainability and green chemistry. We all know that the word green is very popular when it pertains to anything. So now we have green chemistry. So what is green chemistry? There's a whole list of different things that they put in the book that are green chemistry, the tenets or principles of green chemistry. And clearly they pulled this from some other book and they just gave you a list. I just want to summarize the idea of green chemistry. So when you look at that big old list, these are the main ideas: to use and produce materials with low toxicity or chemical reactivity. That way they're less harmful or to people for the toxicity, less harmful for the environment for reactivity. You want to minimize the use of energy. So what that means is you'd prefer to do a chemical reaction at room temperature. You'd prefer to do a chemical reaction at atmospheric pressure, not under high pressure or low pressure, because both situations require energy to maintain that type of pressure. And you want to create few byproducts, okay? Regardless of whether or not the byproducts are harmless or not, you really don't want to have a whole lot of byproducts. Those are your basic ideas of green chemistry. All right. We do practice green chemistry in our class, and we've been doing it forever, because who wants to work with a bunch of toxic chemicals? Not me. All right. Classifying matter. So here's some good meat for us to look at. Understand the basic ideas of kinetic molecular theory. Recognize the importance of representing matter at the microscopic, macroscopic, microscopic, and symbolic levels. This microscopic in my opinion, should really be particle level. And the reason I say that is microscopes are really good for one thing, seeing microscopic things. Atoms and molecules are not microscopic. They're 1,000 times smaller than microscopic. So that means you can't see molecules and atoms in a microscope. You need what would be called a nanoscope. And those are really expensive. Recognize the different states of matter and give their characteristics. Recognize the difference between pure substances and mixtures, and the difference between homogeneous and heterogeneous mixtures. Okay, so let's take a look at what they have in the book. They have this nice chart that I like from the book. Oh, actually, I've jumped ahead. First, they talk about states of matter and the kinetic molecular theory. So this isn't something that you see in the book. This is something that I just kind of put out there on my own to help you understand states of matter. So we have 3 states of matter in this class that we're concerned about: gas, liquid, and solid. We use abbreviations for each of these. For gas, it's a cursive G. For liquid, it's a cursive L. And for solid, it's supposed to be cursive S, but I always use a printed S. Okay, so from the macroscopic view, so this means you looking at it, what do you see for a gas? And here I put these lines through here to show you that the gas is everywhere in the container. Turns out you actually cannot see steam. It's an invisible gas. So that might make you wonder, well, what about that stuff I see coming out of the top of the train? All that steam. It's not steam, it's water. What has happened is the steam has cooled down enough so that it's condensed into small little water droplets, which you can actually see. And what do a bunch of water droplets look like when they're all together? They look like a cloud, okay? What happens when those water droplets separate into their individual H2O molecules? It's invisible, you can't see it. All right. Here, liquid, you can see that I've had this little jagged line up here. That's supposed to be like the waves on top of water. You'll notice that the level of the water is perpendicular to the level, not perpendicular, parallel to the level of the floor. The heat, the ice, you can see I made what looks like a mountain here. And the reason I drew each of these this way is because my description of these is that a gas is something that could be breathed, not necessarily that something you want to do. A puddle is something that you could jump in and would splash around. And a pile is something that you can make out of a solid. You can't make a pile out of a liquid. So I call this my second grader's description of each of these states. Gas could be breathed. Puddle is something you jump in, that's a liquid. A solid is a pile, okay? So what does that mean dogs are? Are the dogs gas, liquid, or solid? Solid, right? Because you can make a dog pile. What do you think dogs call humans piled up together? They call that a human pile? I don't know. All right. Now, from the particle level, that macroscopic level, here's what gas particles look like. They are moving in constant random motion. So random motion doesn't mean the drunken sailors walk, but rather they move in a straight line till they hit something, then they bounce off and move in a straight line till they hit something else. So the randomness is how far they go before they hit something, and then how far they go again before they hit something else. And they can even run into each other and bounce off of each other. But once they bounce off, they just move in a straight line until they hit something else. So that's the randomness. It's the randomness of a almost of a pinball in a pinball machine, except for that's not a very good description, because in a pinball machine, the ball moves in 2 dimensions, not 3. Gas particles move in 3 dimensions. So I normally have an activity during lecture where I make everybody stand up and be a gas. So what would your behavior be like in my room, in my lecture room, if you were being a gas? Think about it. Yeah, it's a little uncomfortable because you don't know anybody else. And yeah, you walk in a straight line until you bounce off the desk. Then you walk in a straight line until you bounce off another desk. Then you walk in a straight line until you bounce off of somebody. And some of you are supposed to be walking slow, and some of you are supposed to be walking fast because the gas particles don't all move at the same speed. And then here's a liquid. The particles are touching one another, and they're moving relative to one another. And here's the solid. You guys see these little quote marks, if you will? They're the same things that you see on Snoopy when he's dancing on his doghouse. So these atoms are vibrating in place. And the description that we often give to these microscopic things, or macroscopic, is constant volume of the container for the gas, shape of the container for the gas, constant volume for the liquid. The shape of the liquid is determined by the container, and we have a constant volume and constant shape for the solid. I've lost someone. I wonder who it was. Let's see if Quinn's still here. No, Quinn's still here. There used to be 14 of you. Now there's 13. All right. So here's the kinetic molecular theory in words. Gases, the particles are in constant and random motion with a lot of space between the particles. And that has ramifications for how gases behave. Liquids, the particles are in constant and random motion with little or no space between the particles. So they're touching. So this would be like the, what do they call that thing where the kids get together at a concert and they all gather together and kind of run into each other all the time? Who knows what that's called?
It's called a mosh pit.
Ah, so a mosh pit would be like a liquid. For me, the liquid would be like waiting to get into a Led Zeppelin concert and you're right there at the doors. That would be the liquid. You with me? Oh, I just gave away my age, didn't I? I'm old. All right. Solids. Particles are not in motion. They vibrate in place. There is little or no space between particles. So in class, I ask people while you're sitting there at the desk, why are you a good example of a solid? And the answer is because you're all sitting in place and you're kind of vibrating in place as you take notes. Why are you a bad example of a solid? The answer is because you have space between you and the next person. Solids aren't like that. Capiche? All right. And then I added this at the end. For substances, the addition of energy in the form of heat causes the change of state from solid to liquid and liquid to gas. So if you want to go from a solid to a liquid, you heat the solid. Just think about ice. How do you get ice to melt? You heat it. How do you get water to turn into steam? You heat it. Okay? And the reverse is also true. How do you take steam and turn it into a liquid? You cool it. How do you take liquid and turn it into a solid? You cool it. So you actually have to take energy away. And you got to put it somewhere. Okay. Any questions about the kinetic molecular theory of gases? Okay, we're going to move on. Okay, I really like this slide in the book. They talk about levels of understanding for matter, but it's basically for chemistry. So when we take a look at the levels of understanding, one of the levels we have is that which you can observe with the eyes. So this is supposed to be a boiling cup of water. And that's right, this is at Hogwarts because that is a levitating cup by magic. This is probably something all of you can appreciate because you're all probably Harry Potter fans. Give me a thumbs up if you're a Harry Potter's fan. None of you are going to admit it? I don't believe that. Okay, so give me a thumbs down if you're not a Harry Potter fan. Give me a no if you don't know how to find the thumbs up and the thumbs down. Click no. Wake up. Come on. If you don't participate, I'm going to stop doing these lectures. Give me a no if you don't know how to use the no. One person? I'll just sit here and wait until we get some more thumbs up and thumbs downs. The question is, are you a Harry Potter fan? So far, the overwhelming majority say no. So if you don't know how to pick your thumbs up or thumbs down, go to your participant list and open it up. At the bottom of your participant list, you should see a list that says yes, no, go slower, go faster, more. Choose more, and you'll see that you got the thumbs up, thumbs down, clap. I need a break. That's the coffee cup. And I'm away from the screen, which is the clock. Kind of like a timeout. All right, don't make me call you out about not using the thumbs up or thumbs down. I'm not afraid to. All right, who's a, what's that other J.K. Rowling's thing? Something fantastic. Who's a Fantastic Beasts fan? So I'm going to clear you all. Fantastic Beasts. Who's a Fantastic Beasts fan? Pretty much the same ratio. You either like JK or you don't. Okay, I got to know, what's the big thing these days for people? Someone's got to tell me. Who can tell me what's the big thing like Harry Potter was? Is there anything out there?
Working remotely, Zooming, Skyping,
That ain't fun.
homeschooling kids.
Oh, well, yeah, I don't know what I would do about that. Okay, let's move on then. So here, the macroscopic is what you see. And this is supposed to be my version of boiling water. All right. Now, we also have the particulate level or the particle level. And here, we're looking inside of one of these bubbles. So inside of one of these bubbles, you have these water molecules moving in a straight line until they hit something else. Now, here's something that's really, really fantastic. When you look at these water molecules, and let's say that this is the bubble right here, what is that wall made of? Who wants to take a guess? So this is a bubble. What's that wall made out of? Happens to be made out of H2O molecules. Can you imagine that? Those gas molecules are contained within an envelope of liquid molecules. And if you're thinking, well, what's to keep that gas molecule from hitting the liquid and popping into the liquid and becoming a liquid molecule? And the answer is nothing. Nothing would prevent it. But then the question would also be, what would keep one of these liquid molecules from coming into this pocket here and becoming a gas molecule? And the answer is nothing. Nothing would prevent it if it had enough energy to be a gaseous molecule. And nothing would prevent this becoming part of the wall if it lost enough energy and became a liquid molecule. So you actually have a dynamic process here where some molecules are becoming gas, some are becoming liquid, but you keep adding energy to this and more molecules become gaseous. The bubble becomes bigger, and eventually, because the bubble is less dense than the liquid it's in, it floats to the top. Notice I said less dense, not lighter than, because that's the mistake. Things that are lighter than air don't float in air. That's just silly. I mean, I don't get it, because if you take all the air in the world and put it into a container, I'm lighter than that, and yet I don't float. So what makes things float? They're less dense than air. So a helium balloon is less dense than air. A rock is more dense than air. Some wood is less dense than water. Ironwood is more dense than water, so it sinks. Okay, so here's the particulate level. Now, we're going to spend a whole lot of time talking about these things and actually drawing these things, but ultimately, when we want to communicate efficiently, and we want to communicate quickly, and we want to communicate in a way that is universally understood. So there's the symbolic language behind chemistry, and this is the symbolic language. So this says that H2O liquid is turning into H2O gas, or in simpler words, water is boiling into steam. Okay? So any questions about the symbolic language? That's something that you are going to have to learn. All right, moving along. So this is the real tough thing that we have to do today. Classification of matter by composition. So this is the flow chart that's in the book. The flow chart in the book is kind of spread out horizontally and goes down. I made mine go to the right. And this is on purpose. This is to make you think about this rather than just repeat what they have in the book. I'm going to present it to you just a little bit differently to make you think about it. Okay, so we start here on the left and we start with matter. So all of this stuff here to the right is a type of matter. Matter is anything that has volume and mass. Regardless of whether it's easy to measure the mass. So it could be something really large like the moon, definitely massive. It can be an electron. An electron has mass. Matter, anything with volume and mass. I can't think of anything that has mass that doesn't have volume. Everything that has mass has volume. I can think of one thing that has volume but no mass, and therefore it's not matter. And that one thing is something called space. Space is a volume with nothing in it. We also use the word vacuum for that. So space and vacuum are the same thing. I'm not talking about outer space. I'm talking about just the chemical definition of space. Space is a volume with nothing in it. Okay, so space is not matter. There are two types of matter based on whether or not the properties are consistent throughout the matter. So let's say you take that matter and it's a solid and you put it in a pan and it all melts at one temperature, all at the same time. You take that matter and you continue to heat it and it all boils at the same temp. You put a little thermometer in there, you watch it boil, and it boils at the same temp. This is something that seems to have the same properties throughout. You take that matter and you put it in water and it doesn't dissolve. You take that matter and you put it in gasoline and it does dissolve. So once you start testing a whole bunch of properties and you find out it's the same for that matter, regardless of which portion of the matter you use, you're thinking you have a pure substance, okay? So here, this is what all of this means. Matter of one type, single set of properties. Now let's say that you put a different type of matter into a pan and you put your stove on and some of it melts and some of it doesn't. Well, now you know you have a mixture, because if it were matter of one type, it should have all melted or all not melted on the stovetop. If some of it melted and some of it didn't, you've got a mixture. Two different sets of properties. Okay, now when I say set of properties, some properties may be the same, but the whole set will not be the same. So you can have two solids that would not melt in your stovetop, but then you take the mixture and you put it into water and one of them dissolves and the other doesn't. For instance, if you took a mixture of sand and salt and put it on your stovetop, you wouldn't be able to melt either of them. But if you put it into water, the salt would dissolve and the sand would not. So you have matter with two different sets of properties. That means you have a mixture. So how do you go about trying to determine if you have a mixture or a pure substance? I want you to think about the answer. The question is, how do you go about determining if you have a mixture or a pure substance? Once you think you have the answer, give me a thumbs up. And don't worry, I'm not going to call on you. Just give me a thumbs up if you think you have the answer. Okay, so I'm assuming if you don't have your thumbs up, you're still kind of wondering, how do I tell? So I'm gonna spill the beans. Here's what you would do. You would try to melt it and see if it all melted at one temp. If it were liquid, of course you wouldn't try and melt it. You try to boil it and see if it all boiled at one temp. And then you take a little bit of it and see if it dissolves in water. If some of it doesn't, it's a mixture, and so forth and so on. You would do simple things like that. And this is one of the things that people have trouble coming to grips with. You come into a class called chemistry and you think, dang, it's got to be hard. I've got to come up with some sort of clever, unique way of doing something. And the answer is no. We're trying to teach you the foundations. So the stuff I'm telling you is the answer. You would try to figure out whether you had a mixture of pure substance by trying to do things to it. Now, there are some mixtures that you wouldn't even bother doing what I just described. So let's take a look at two types of mixtures. One type of mixture is the homogeneous mixture. The other type is the heterogeneous mixture. And these are as simple as can be, in that when you look at them, a heterogeneous mixture does not look uniform. A heterogeneous mixture does not look uniform. If you want to see a heterogeneous mixture, look in a mirror. You do not look uniform. Your hair does not look like your eyes. Your eyes do not look like your skin. Your teeth do not look like your lips. You are definitely a heterogeneous mixture. If you were a homogeneous mixture and you looked in a mirror, you'd be looking at one of those scary store mannequins. You know what I'm talking about? Yeah, they look homogeneous, consistent throughout. So what are the things that are homogeneous that we can describe? Many of your beverages are homogeneous, like Coca-Cola, Pepsi-Cola, carbonated beverages, milk. Milk, if you buy it in a store, it even says homogenized because they make it homogeneous. Milk from the farm is heterogeneous. You have the froth on the top and the cream on the top and the milk on the bottom. So you can basically just look at it. If it looks the same throughout, it's homogeneous. And a lot of the homogeneous things I've described to you are liquids, not solids. It's really kind of hard to think of homogeneous solids, to be honest, unless you go into a hardware store and you see a bolt made out of iron, then that's homogeneous, or something made out of aluminum, okay? But for homogeneous, we're usually looking at liquids. Let me see, I gotta do something here. Boom, boom, there we go. Okay, so you're heterogeneous. Homogeneous might be a piece of paper, a soda, but it has to be a mixture. Is sugar homogeneous? And the answer is no. Why? Sugar's not a mixture. Sugar is a pure substance where if you put it on the stovetop, it'll all melt at the same temp. It'll all dissolve in water. It will not dissolve in gasoline. Okay, moving along. Now, let's look at pure substances because that's the opposite of a mixture. Pure substance, matter of one type. Now, for this matter of one type, there are two types of pure substances. There's the compound and there's the element. And the idea with a pure substance is that if you can do something chemical to it and separate it into two different things or more, you've got a compound. So a compound is essentially two or more elements that are chemically combined, not physically combined, chemically combined. And so what that means is that the atoms of the elements are bonded together either through something called a covalent bond or an ionic bond. Now, those aren't written down here because that's going to be a big topic of a future chapter. Elements means that all the atoms are of the same type. And we'll learn exactly what it is about an element that makes it that type of element. Why hydrogen atoms are hydrogen atoms and how we can tell them from helium atoms, okay? So what are the types of chemical separations you could do? These I don't have written down, but you may want to write them down. One type of chemical separation is electrolysis. So you could run electricity through the sample. And what that often does is it allows you to separate two different elements from a compound. You can also do other things like oxidation. You can do acid-base reactions, precipitation. So there are a few ways to chemically separate things. All right, so that's classification of matter by composition. If we go back, we could call this classification of matter. Classification of matter by what? By state, okay? So there's many ways of classifying matter. And what we just did was classifying the matter by how it is put together, composition. Okay, the next section is about elements. I think we're gonna finish up with compounds today. And on Friday, we'll finish up the chapter. But let's go ahead and finish this up. So, elements. Goals. Identify the name or symbol for an element, given its symbol or name. So what they mean here, I don't like the way they wrote this, but it does make sense. Identify the name if given its symbol, or the symbol if given its name. And use terms atom, element, and molecule correctly. So before we go into any sort of definition here of what these are, I want to show you your book and your periodic table. So here it is. Let me see if I can show you the whole darn thing. Nah, I can't. So let me get you a smaller periodic table. I have to go up and get it. Now, I'm going to provide you with a periodic table that I'd like you to print. It's not available for you yet, but I'll make it available this weekend. So here's your periodic table. And this is a lot like the periodic table I'll supply to you. All the elements will be in order. You'll see the symbol for the element, but you won't be able to see the name of the element. And you'll also see the number on top and the number on the bottom. Okay, so for instance, this element here, Ni, with a 28 at the top and a 58.69, it looks like at the bottom. You'll be given all of that on the periodic table I give you. And you're allowed to use that on every quiz and every test, except for the lab safety quiz, which you're going to be taking on Friday. Since you're going to be given this periodic table, but not the names, you will need to memorize some of these names. So, what names should you memorize by next week? Do you see this number at the top here that says 1? And this number over here on top of helium that says 2. And then on top of lithium it says 3, 4. So looking at those numbers, by this time next week, you should know numbers 1 through 36. You should know the name for each of these symbols. For instance, you should know that H is hydrogen. He is helium. Li is lithium. Be is beryllium. B is boron. C is carbon. N is nitrogen. A lot of these I think you already know. You probably already know sodium and magnesium and aluminum and silicon. This is silicon, not silicone. So this is not the stuff that you caulk your tubs with. You probably know phosphorus, sulfur, chlorine, and argon. You probably know potassium, calcium. Scandium may be new to you. Titanium you do know, I'm sure. Vanadium may be new to you, unless you have tools that are coated with vanadium. Chromium you probably know because your toaster very well may be chromed. Manganese you may not know. Iron I'm sure you know. Cobalt you probably have heard of. Nickel, copper, zinc. These are interesting ones, gallium and germanium. This one sounds like it was named after Germany because it was. As is arsenic, selenium, bromine, and krypton. Okay, so make sure you memorize those by this time next week. And then after that, I'm going to add probably another 20 that you should memorize because they are commonly used in chemistry classes. For instance, this guy right here, Ag, silver. Au, gold. Hg, mercury. Those are ones that you should know. You should definitely know this guy right here, U, uranium. Okay, and Pu, plutonium. Common ones. I'm not going to have you memorize the ones that you're probably never going to run into in your life. Like, for instance, as cool as it may sound, where is it? I think it's this one, protactinium. It's just got a cool sounding name. Okay. All right, moving along. We're going to try and wrap this up in the next 6 minutes. So let me back out so that you can see what's written here. All right, atom, smallest particle of an element that has the properties of the element. Molecule is a pure substance where 2 or more elements, atoms, are chemically bonded together. So the difference between a molecule and an atom is that a molecule is made out of 2 or more atoms. And they're different atoms, meaning they're different from different elements. For instance, nitrogen is made out of 2 atoms of nitrogen, but it's not a molecule, technically, because it's not 2 different elements. Element, type of substance, pure, where the smallest unit is an atom, and the atoms have the same set of properties. And here I put down the same set of chemical properties because it turns out that atoms of an element may have slightly different physical properties. And we're going to get into that in a future chapter when we start talking about something called isotopes. And that's probably going to be in chapter 2. Okay. Boom. Compounds. The goals of this are to use the term correctly, understand the law of definite proportions, also called the law of constant composition. So here, when we start talking about compounds, really for the law of definite proportions or constant composition, whichever you want to call it, this context is relative to something called a mixture. So we know a mixture is 2 or more substances, each with its own set of properties. Compounds have a discrete formula. That means that the ratio of atoms of elements is known. So for instance, H2O, and by the way, when we say H2O, this means 2 atoms of hydrogen and 1 atom of oxygen. So here the numbers describe how many of the element in front of the number, not behind it. So this again means 2 hydrogens, 1 oxygen. This is a compound. It has a discrete formula. There's another compound that's very similar to H2O, and it's called H2O2. It's got 2 atoms of hydrogen and 2 atoms of oxygen. And because the ratio is different than the ratio of H2O, it's a different compound. So the top one, in its standard state, we just call it water, right? Standard state at room temp. This stuff we call hydrogen peroxide. So these 2 compounds have very different chemical behaviors. You know, you bleach your teeth with hydrogen peroxide. Back in the day when I was a kid, there were some people who used to bleach their hair with hydrogen peroxide. Not a very good idea. You don't bleach your hair with H2O. You get a cut in your mouth, you rinse with H2O, hydrogen peroxide. I just went to the dentist, and one of the precautions they take is they make you do a hydrogen peroxide rinse for about 30 seconds to kill anything in your mouth that may come out and get them sick, which kind of makes sense. Okay, so because each atom has a particular mass and there's a particular ratio of atoms in a formula of a compound, they have a discrete percent composition by mass. So if we take a look at each of these, let me just do this real quick on my calculator. So for water, it is about 89% oxygen by mass, and it's about 11% hydrogen by mass. Whereas over here, we're talking about 94% oxygen by mass and 6% hydrogen by mass. So that's a constant composition, okay? Now mixtures, on the other hand, have 2 or more substances in it, and each substance has its unique set of properties, and you can have a different percent composition. One of the things I didn't think of to do, but now I am thinking of, you can actually buy a mixture of water and hydrogen peroxide. So the stuff you buy in the store is 3% hydrogen peroxide. So that's 3% hydrogen peroxide by mass, 97% water by mass. That's the stuff you buy in the store, because any more concentrated than that, and it's very dangerous, highly reactive, not very green. In our stockroom, we can buy the 35% stuff, but that's the kind of stuff that you want to have some training to be able to handle safely. The difference between 3% and 35% is night and day. So the deal here is that when you have a mixture, there is no discrete percent composition. It changes. It depends on what you put together. So that's the difference between a compound and a mixture. Compound, law of definite proportions, constant composition, constant mass by percent. Mixtures, they don't have a constant mass by percent. So that's how you tell the difference between a compound and a mixture. All right. And we end up with where we began, how to study chemistry. So I didn't record this because I didn't put my record button. So we get to see this again. Daily, better to keep up than catch up. Don't cram. Write out answers. Do sample problems. I want to talk a little bit more about this doing sample problems. At the end of every chapter, there are a whole bunch of problems. You should do as many of the problems as you can that have answers in the back of the book. Having answers in the back of the book gives you confidence that you're doing the problem correctly. You can also, if you want, buy a solutions manual that probably has all the answers. A lot of the questions I'm going to be putting on your homework assignments are going to come out of the back of the book, but they're not going to be the one with answers in the back. They're going to be the ones that don't have answers in the back. So you might be thinking, darn, I'm going to get that solutions manual so I can get a perfect score on my homework. That's fine and all, but it's only 5% of your grade. And if you get the right solution for your homework on the homework, but you don't know how to do it, that's going to give you a 0% on your test. And the tests count for, including the final, about 50% of your grade. So the trade-off is, yeah, I get a perfect 5% for my homework, and I get a really low percentage on my test because I really don't know how to do these problems. Part of learning chemistry is to struggle with it. If you're one of those fortunate people that don't struggle, you just get it, more power to you, that's great. But most of us are going to struggle. I took chemistry at CR, and I had to spend many hours a week studying chemistry. Luckily, back then, I didn't watch TV. Okay, ask questions and be prepared one day early. And that includes for lecture. So if you haven't already read through all of those lecture slides in chapter 1, which are posted in module 1, you want to make sure you read those because I'm going to finish up chapter 1 on Friday. So that being said, unmute yourselves. Unmute yourselves. Oh, maybe I can unmute you all. Cancel. Unmute yourselves and say goodbye.
Bye.
Bye.
Bye. Bye-bye.
Bye.
Everyone.
Thank you.
Have a good day.
Yep.
Have a good day.
Bye-bye.